Hi everybody, my name is Sai. I'm a master's student with the Minnesota Robotics Institute, which is part of the University of Minnesota. Today I'm going to be explaining our paper titled MambaTron and using it to perform efficient cross-modal point cloud enhancement. So MambaTron is basically an aggregate selective SSM, and SSM stands for state space model. I'll be explaining that soon. So first I'm gonna talk about the task. Point cloud enhancement or point cloud completion is the task where the model takes in a partial point cloud and tries to complete it, either by perturbing the existing points or by upsampling the entire point cloud. Point cloud enhancement is more like an umbrella term. It incorporates point cloud denoising, point cloud and upsampling, and point cloud completion. For the scope of this presentation, I'm gonna be mostly referring to point cloud enhancement as point cloud completion. So, cross-modal point cloud enhancement. This is the process where the model tries to complete a partial point cloud, but at the same time it's also given a reference image. So the reference image has some information that can be used by the model to complete the point cloud. The reference image is complete, unlike the incomplete point cloud. Alright. So the task of cross-modal point cloud enhancement was introduced by VIPC, which stands for View Guided Point Cloud Completion, which was introduced by Zhang et al. The paper goes by the same name. So the current state-of-the-art methods for this model are XMFnet, which stands for Cross-Modal Fusion. So this model mostly incorporates cross-attention between the image and the point cloud, and it does a few other things as well. And the second state-of-the-art method, which kind of surpasses XMFnet as well, is EGNet, which came out last year. And this thing uses something called a style transfer mechanism, which was initially introduced for image art generation back in 2015, I believe. And the things that are common between these models is that they are mostly transformer based architectures, which basically use some sort of attention to perform the task. So let's talk a little about transformers. I won't go into the details of how they work, but the advantages are, first thing, they're great at language modeling. That's what they were initially introduced for language translation tasks. And they are also good at 2D and 3D vision tasks. So shown by the vision transformer and point cloud transformer papers, among many others. There are some disadvantages as well. The first thing is that they have a hard context limit. Once you cross that context limit, even in theory, the transformer cannot produce any more data. It will start hallucinating. And it takes O of L square computations, where L is the length of the input sequence. So can we do better than this? There are improved architectures which mostly scale the context by a factor of 10 or 100 or 1000. So the first one's transformer XL. The second one's something called block transformers. This is a model that came out very recently. I think it came out in 23 or 24. And finally we got block recurrent transformers. I won't go into details of all of them, but the thing is all of them have something in common once again, and that is recurrence. We'll mostly be talking about block recurrent transformers though, because MambaTron is based mostly on that. So, block recurrent transformers. This is basically the diagram of how it looks like. I will explain how it works, the outline at least. So it's got something called an output block, which gives you the final output, and you got something called a recurrence block. So the way it works is it uses something called a state, and as it traverses through an input sequence, it updates that state, and using the current input and the current state, it tries to calculate the output. So as shown here, xi is the input state, hi is the latent state, and yi is the output. It should be noted that regardless of the lengths of the input sequence or the output sequence, the size of the latent state stays the same. So that's an important thing in recurrence. So coming to properties, first thing, block recurrent transformers operate on a sliding window which is of size W instead of the entire sequence. So this window is usually way smaller than the entire sequence. It is fixed. For example, if the sequence length or context length is somewhere like 1024 or 4096 or something bigger, the window size is something much smaller. For example, 64 or 128 or something like that. And it uses recurrence, which is done using the sliding window. And it has no hard context limit because instead of using attention directly, it uses a latent state. And no matter how big the input sequence is, the latent state size stays the same. And as shown by this point. And it's got O of LW computational complexity. Compare that with O of L square computational complexity for vanilla transformers. So LW tends to be way smaller than L square. And that means block recurrent transformers are significantly more efficient compared to vanilla transformers. So there are some disadvantages as well. The first thing is using the same recurrence, the concept of recurrence. The concept of recurrence was a plus for this model, but at the same time it's also not parallelizable, meaning you have to traverse the entire sequence to get the n+1th character or something like that. And it's got a small, if the window size is small, it tends to be really slow because it has to slide the window throughout the entire sequence. And if the window size is large, the memory usage explodes because the memory size is directly dependent on the window length. The latent state is directly proportional to the window length. You can say that, yeah. But there's a solution to this, at least a partial solution, and that is using the MambaTron cell. I'm gonna explain the details about the MambaTron cell. So first, take the block recurrent transformer, replace the recurrent cell. Remember I told you there's an output block and a recurrence block or a recurrence cell. Replace the recurrence cell with a Mamba block and parallelize the input blocks instead of using a sliding window. So the Mamba block parallelizes everything while the recurrence block doesn't. I'll explain this soon. So this is the block recurrent transformer. It's got an output block and a recurrence block. Replace the recurrence block with a Mamba block. So this is how a Mamba block looks like. It basically contains some linear layers, a convolutional layer, a SILU or a swish activation layer, and there's something called an SSM, which stands for state space model, there's a multiplication operation, and there's another linear layer. So this is the vanilla Mamba block. We won't be operating using this one directly. We'll be making a few tweaks to make it suitable for computer vision tasks, especially 3D vision tasks. So first I'm gonna talk a little about what an SSM layer is and how it works. So an SSM layer tries to solve two linear equations. So X stands for X is the input sequence, Xi is the ith input state, H is the latent state as described before. A, B, and C are basically the parameters of the SSM. B and C are dependent on the input, so Bi and Ci, you could say, depends on Xi. Whereas A is a square matrix. All right. So the SSM or X6 layer. So S6 stands for SSM with a selective scan. It's a long abbreviation. The Mamba block uses the S6 layer, shown by SSM, where Xi is the ith input, Hi is the ith latent state, which incorporates the accumulated context, and Y is the ith input, similar to the block recurrent transformer. And ABC, as mentioned before, are trainable parameters. So this is a simplified diagram of how an SSM operates. First, it calculates H0. Through H0, it calculates Y0. It also calculates H1. Through H1, it calculates Y1, and so on. So we call it a forward SSM because in computer vision tasks, you're gonna need a forward SSM and a reverse SSM. The performance of a state space model greatly depends on the way in which the input elements are scanned. So for 3D vision tasks, you need to scan both ways and get outputs both the ways and operate on both of them. So Y is the sequence obtained by scanning it forwards. Q is the sequence obtained by scanning it backwards. So this is the MambaTron cell. So on the left you see the Mamba layer. It's mostly based on a different model called Point Mamba, which is in turn based on the vanilla Mamba block, which was intended for natural language processing tasks. So it basically has a layer norm. You perform normalization before passing it further, and then you downsize the input embeddings. So the input embeddings are typically of length 64. You downsampling it to either a length of 32, which we used, or you can even bring it down to 16. And then you perform a depth-wise convolution on the left side, and there's a swish activation function or sigmoid linear unit on the right side. And after passing through the SSM, the outputs of the forward SSM and the reverse SSM are added together, and then there's a linear layer that upscales it back to the length of 64. And then you pass it through something called the block transformer layer, which is basically the output block of the block recurrent transformer. So some properties of SSMs: they got a fixed size latent state similar to block recurrent transformers, and the computational complexity is given by the following. Mamba has basically O of L log L operations. In some cases, in certain tasks, it can go down to O of L even, where L is the length of the input sequence. Compare it to transformers where it's O of L square, or block recurrent transformers where it's O of LW. So here's the operation on how MambaTron works with the input sequence. The Mamba layer and the transformer layer, they don't operate exactly equally. The Mamba layer operates on the entire sequence, while the transformer layer, it operates only on a set block. For example, here you can think of the block size as 4. It operates on 4 inputs at a time. It's similar to the output block of the block recurrent transformer. It doesn't operate on the entire sequence, it only operates on a sliding window. And the transformer blocks that operate between different input blocks, they all share the same parameters. And the transformer operation is parallelized. The Mamba operation is sequential, but it's fast. The transformer operation is parallelized, number one, and number two, it is parallelized. And number two, the context size is minimized because the context size is now W square instead of L square compared to vanilla transformers. So W square doesn't increase with the input sequence length. That is an advantage. So like I mentioned, MambaTron cells are bidirectional, which I explained before. The transformer block is fully parallelized versus the recurrence in block recurrent transformers. And like block recurrent transformers, it has a fixed size latent state, and the overall computational complexity is given by O of L log L for the Mamba layer and O of W square for the block transformer layer. So O of W square is typically way smaller than O of L log L. So O of L log L is the bottleneck, you can say, for this operation. And like I said, W is usually way smaller than L. So coming back to our task, once again, point cloud completion is the task where you take an incomplete point cloud and try to finish it. Cross-Modal point cloud enhancement does the same thing, except it also takes a reference image as an input. The image is not cropped or anything, it is complete. So we'll talk about the task pipeline. So we got something called an initial tokenizer, and then we got intramodal encoders, a cross-modal encoder, and a completion decoder. So the MambaTron cells are only employed in the intramodal encoders, which operates on only one modality, and the cross-modal encoder, which operates on all of them. So a few things about the initial tokenizer. The input image is divided into M-cross and patch features and is processed using something similar to a vision transformer, or even a convolution operation is good enough. And the input point cloud is, it undergoes a series of steps. The first thing is called FPS, or farthest point sampling. The second is K nearest neighbors. So farthest point sampling samples a set of center points, and then K nearest neighbors calculates a set of K points for each of these center points, which gives you a set of smaller point cloud patches. And then each of these patches is turned into a directed graph for sequencing purposes. This is a well-established technique which we also decided to use, and it gives you point cloud patches as described. So coming back to the task pipeline, there's something called an adjacency preserving reordering layer, which is shown by the brown layer here. That is necessary before we pass the point cloud embeddings to the intramodal point cloud encoder, the MambaTron encoder, because when it comes to processing point cloud patches using a Mamba block, ordering is very important. So we just used a parametric layer which decides on its own which way is the best. So the thing is, regardless of what order it chooses, there is one guarantee: all the adjacent points, or all the adjacent embeddings in the final reordered group embeddings correspond to point cloud patches which are geometrically adjacent to each other. It is shown by this block. Since we don't have too much time, I won't go into too many details. So, coming to the experiment. We used something called the ShapeNet VIPC dataset. It is based on the ShapeNet dataset, and it was introduced by Zhang et al. As described before. The paper which also introduced this task. It contains ShapeNet objects and also some reference images for these objects. It's an extension of the ShapeNet dataset. So, training loss. The total loss is given by 3 losses actually. So the first one's the 2D reconstruction loss. The CD loss is called the chamfer distance loss, which is the 3D reconstruction loss. And then we got something called the style loss or the style transfer loss. So first, this is the chamfer distance loss. So the way you calculate it is, chamfer distance is basically when you take 2 point clouds, you superimpose them, try to make the points as close to each other as possible, and then for each point in point cloud A, you find the point in point cloud B or P2, which is the closest to the set point in point cloud P1. You do that for each point in P1, and then you add them up together, or add the squares together. You do the same for point cloud P2, and then you sum them up. That's basically the chamfer distance loss. And then the 2D loss, it's a well-established loss in image generation tasks. It's basically the mean square error between the output image and the input image. So this is the style transfer loss. It was introduced by Gattis et al. Back in 2015 for image art generation. So it features something called a gram matrix. So gram matrix is given by this equation. Basically you take a feature vector and you multiply it by its own transpose. So if the feature vector is of length n, the gram matrix is a square matrix of length n cross n. So basically what we are trying to do is we are trying to equate the gram matrix of the image features to the gram matrix of the point cloud features. So you, yeah, that's it. So finally here the results after training. So these are all objects from the ShapeNet VIPC dataset, and these are the outputs. And numerically speaking, here are the results of our model. Our model performs on par with the transformer based architectures like EGNet and XMFnet, while also trying to be more efficient than them. So this is on the known categories. These are the categories that the models trained on for the same task. And so these are the results for the novel categories. These are not the models that these are not the objects that the models trained on. And as we've shown, our model performs even better on novel categories compared to the non-categories. So yeah, that's the gist of it. That shows how well Mamba is capable of generalizing given the right architecture and the right setting. So yeah, that's the end of the presentation. And if you have any questions or would like to discuss something with me, I'm ready. Thank you very much.